In this chapter, we're going to spend our time analyzing quadratic functions. In this lesson, we'll quickly review what we mean by the word function, and then we'll introduce what is meant by a quadratic function.
Okay, hi everybody. So in this lesson we're going to take a look at quadratic functions. Okay, and to be honest with you, this is one of my favorite topics in high school math, is when we start talking about functions and some of the theory behind it, and the ideas that we build our understanding of functions on. It's kind of like, you know, having a car and looking underneath the hood to see how things actually work. We're going to do some definition work here. Make sure that some of the more fundamental concepts make sense to you, and then we can build on that. Really important, like to me personally, that my students understand the concepts that we go over here. So a comparison between two sets of data is called a relation. Okay, and so that's exactly, the word relation is the perfect word for that. Okay, it's the relation between two sets of data, and a set of data is just that. It's just a group of values. It can be more than just values here. A relation doesn't have to be necessarily mathematical in terms of numbers and whatnot. It can be anything really, but it's just a relationship between two sets of objects. And we can represent this relationship between two quantities in many different ways. You can use words, table of values, ordered pairs, an equation, a graph. There's lots of different ways to represent these. So what's important is that relationship though. So let's take a quick look at these two examples here. So we're going to use the equations, okay, to complete the table of values here. And in a second here, we'll take a look at what the graph looks like when we put it on the grid here. So, and take a look at this. Y is equal to 3x plus 5. Now, bear in mind, x is the independent variable, which means you get to choose the value of the independent variable, okay? Or typically when you're thinking about it in terms of the coordinate plane, I'm going to plug in basically every value that I possibly can into the coordinate, into the independent variable here. And what I'm interested in is how the y coordinate depends on the x coordinates. That's why y is the dependent variable. In many ways, working with a function is kind of like working with an experiment, where you've got the manipulated variable and the y coordinate here represents the responding variable. Now, it's really important to me personally that you catch what's going on here. When I build this table of values, okay, I'm building points. I'm building x and y coordinates. But what I want you to catch out of this is that when I start talking about x comma y, okay, on this graph right here, what I want you to get here is that y is the dependent variable. It depends on x. In this particular case, how does it depend on x? Well, y is equal to 3x plus 5. Okay, I multiply this x coordinate by 3 and then I add 5 to get the y coordinate. This 3x plus 5 is the y value. Okay, sometimes when I'm talking to students about this and we're discussing the relationship here, it becomes very clear to me that as soon as they saw the x there, they got the impression that this was x. Okay. But this isn't x, this is x. That letter right there is x. This whole thing here, expression, is equal to y. There is a difference there. So now I can use this idea to build my y coordinates here. How do I get the y coordinate if I know what x is? Well, I multiply by 3 and add 5. So 3 times negative 3 is negative 9, plus 5 is going to be negative 4. Okay? 3 times, when x is negative 1, 3 times negative 1 is going to be negative 3, plus 5 will be positive 2. Okay, when x is 1, 3 times 1 is 3, plus 5 is 8. When x is 3, 3 times 3 is 9, plus 5 is 14. And when x is 5, 3 times 5 is 15, plus 5 is 20. And so now we've got this table of values, this representation of how the y coordinate depends on the x coordinate. Now, that dependence is not totally obvious here. Okay, it's much clearer here, but this at least gives me a sense of how the values are related to one another. And now what I can do is I can graph that okay, on my coordinate plane here. So I know that when x is -3 and I go horizontally over here -3, I'm going to get -4 as my y coordinate. Now it turns out that's actually off the grid for me. It's probably going to be down here. But -1, 2 is going to be right here. 1, 8, okay, is the point right there. 3, 14 is right there. And 4, 20, oh sorry, 5. Oops, and 520 once again is off my grid here, which is too bad here, but 520 would be like somewhere over here. Okay? Now, these are the points that I see from my table of values, but these are just a selection of the points here. I could connect those dots there because I could choose values for the independent variable anywhere, any kind of value, and I could connect all those dots in a line like that. Every point along this line is going to satisfy that equation. Okay, and so this is now a visual way of seeing this relationship. And notice the kind of graph that we're getting right here, okay? This is a straight line graph, and there's a good reason for that. I'll just label that with y is equal to 3x plus 5. So there's my visual. Now I'm going to come over here. Let's take a quick look at this. Different sort of a graph. Notice that now my equation, or my function here, is y equals x squared plus 4. So now my relationship is this. Once I've determined the value of x, I can get the y coordinate by simply squaring that value of x and adding 4 to it. Okay? So this is the relationship. This is the y coordinate. So here's my table of values. So in this case here, when x is -4, I'm going to square -4 to get positive 16. And then I'm going to add 4 to it, and that's going to get me 20. Oops, sorry about that. Things happen. Okay, so if x is -2, -2 squared will be positive 4 plus 4 is 8. I love this one. 0 squared is 0 plus 4 is 4. 2 squared is 4 plus 4 is 8. Now look at that. That's interesting. That is one of the properties of a quadratic when we square something. Because whether you square a negative or square the positive, the result is going to be the same value there. So 3 squared is going to be 9 plus 4, it will be 13. 4 squared will be 16 plus 4 is 20 again. So again, we've got these similar results here. Now when we plot these, -4, 20, it's going to be up here. -2, 8, be right there. 0, 4, 2, 8. There's some symmetry there. Notice it comes down and then it goes back up. 3, 13. Oops, I missed that. 3, 13 right there. And then positive 4, 20. Okay. And actually, I know, because I know that x squared is going to treat the positives and the negatives the same, I can also kind of intuit here that when I go -3, I'm just going to go up to 13 as well. So there's this beautiful little bit of symmetry here. Now I'm going to try to connect this. I'm going to try to do this in a way that makes this look okay. Okay. Drawing the nice curve here is always a little difficult. That's okay. You get the idea. That is sort of what your quadratic is going to look like here, okay? So here's my quadratic function. If I think about what all the points are in between the given points my table of values are going to do. And so this is the equation y equals x squared plus 4. So now I'm guessing at the points in between, but that's a pretty good guess, okay? If I was to find more points, they would lie on that line right there. So let's go through now and finish up some of the information about these graphs here. I'm going to zoom in a little bit. So a linear graph of degree 1, and what we mean by degree 1 here is whether you go to the y variable or the x variable, the degree or the exponent on those is both 1. So that's degree 1. And this looks like a straight line. Whoops, straight line. A quadratic, on the other hand, is a degree 2. And that's because when I go to my x here, my y, this is y to the 1, and that's okay. The larger exponent is the squared. In fact, the largest exponent here is that square on the variable. So this is going to be quadratic. And this has got kind of a U shape to it, but we call it a parabola. Okay, and in fact, if you take science, take some physics here, you're probably going to spend a fair bit of time talking about parabolas because they are really special in understanding projectile motion and optics, understanding lenses and mirrors and whatnot. You do a lot of work with parabolas. So they're an important shape here. Okay, so the domain of a relation, so now we're getting into some of the nitty-gritty here. The domain of a relation is the set of all possible values for the input or independent variable x. The set of all possible values. Every possible value that I can plug in. So basically what I'm asking, when I ask for that, is I'm saying, when you look at this 3x plus 5, are there any values for x that I can't use, or can I use all of them? Same thing with x squared plus 4. Are there any values that I'm restricted from using here? Because if I am, that's important. That's an interesting property of that graph here. So that's about the input value, or the independent variable. The range, on the other hand, is the set of all possible results for the output, or the dependent variable. And that one is maybe in some ways even more important because I'm always interested in what's going on with the dependent variable. How does the y coordinate depend on x? So when I use these specific x values, what y coordinates am I coming up with? And if I give the set of all possible or all resulting values of y, that's the range. Now, let's zoom in again here. For the linear graph, the domain is all reals. And so the way we write that, and I'm going to drop a little bit of the formality here and kind of get right to the meat of it here. Symbolically, what we'd say here is we would say that x is an element of the reals, okay? Because when I look at my graph here, there is no value of x that would be excluded from this. I can take any number I can think of, any real number I can think of, multiply it by 3 and add 5 to it. That's not a problem, okay? And that's essentially what this means here. All the values of x that I can use are in the set of real numbers. Now, I'm using an R with an extra line in it. When you see that extra line in it, that typically means that the letter that we're looking at refers to a set of numbers, whether it's the integers, the real numbers, the rational numbers, whatever. An extra line in the symbol means that symbol is very specifically being used for sets of numbers. And this kind of a weird little E there, okay, that means x belongs to the real numbers. So just a nice general way of saying that x can be anything. Now the range here is all of the y coordinates. And when I look at my graph here, well, it goes down infinitely and it's going to go up infinitely. So when I think about all of my y coordinates, and they're represented along this vertical line, there will always be a point to the left or the right of my y-axis. No matter how far up or down I go, there's always something on one side or the other. So really, my range is going to mirror my domain here. My range will be y is an element of the reals. Now let's take a look at the quadratic. With the quadratic, let's think about this. Are there any restrictions on the variable x? Is there any number that I cannot square and then add 4 to? Think about it a little bit. Well, no, I can square any number. Okay, so let's zoom in again. So for the quadratic graph, the domain is just the same. It's all reals. Okay? If I go left and right along my x-axis here, there will always be a part of this graph that's either above it or below it. Now in this case, there's always going to be a part of this graph that is above the x-axis, no matter how far I go to the left and right. But let's talk about the range. Okay? Let's talk about the range. Maybe let's zoom out just a little bit on this one. Notice that my y-coordinates, if I scan up and down along the y-axis and I look to the left and the right, well, way up here, there are points along the graph to both the left and the right of the y-axis. And that's true until I get down to here. And then all of a sudden the graph stops. There is no graph below the -4 point on my graph here. There is no function down here, which means this entire graph exists from the y-coordinate +4 and up. There are no points on this graph below +4, y equals +4. And so that's how I write my range. The range is going to be all of the y-coordinates that are greater than or equal to +4. Okay. Okay. Now I've been throwing around that word function a little bit loosely here, kind of assuming that everybody's on board with me. Let's just go back and make sure that that makes sense here. So a function is a very special type of relation, and a relation is basically anything that can be graphed. Anything that can be graphed, okay? At least in the math context. It does have a broader meaning than that, but for us in this course here, if you can graph it, it's a relation here. But a function is a very special one of those relations in which every element in the domain is related to exactly one element in the range here, okay? So every x-coordinate, if you want to think of it like that, every value along the x-axis produces only one point, okay? Just one point, which is why you can use the vertical line test to determine if it's a function. So if we take a quick look back at the two graphs we were just working with, whoops. If I take a vertical line and slide it along this curve here, or curve, I use the word curve really in the kind of the general sense here. Anything that can be graphed is called a curve typically. But if I slide my vertical line along here, I always hit this line here just once. Just once. Even same thing with the parabola. As I slide this line across it here, I only ever hit the parabola once. Okay? Now, compare that to something that would maybe look like this. If I had a parabola that lay on its side, well, as soon as you slide a parabola over that, now you're going to immediately hit a spot here where you're going to hit the parabola twice with a vertical line. So this is not a function. Okay? The best we can say right now is that would be a relation. Now, are the previous graphs functions? Yes, they are. The next thing I want to make sure that we're comfortable with is this idea of function notation, okay? So, and I want to make sure that this is really clear to everybody. This is pronounced as f of x or f at x, okay? F of x. And these symbols all together take the place of the dependent variable, okay? F of x is the dependent variable. Okay. Now, it consists of a couple of pieces. I've got f here, and then I've got the parentheses with the x inside. Now, it might look like that I'm making this notation a little bit more awkward because, I mean, isn't that really just the y variable? And, well, yeah, it is, but there's some benefit to writing it like this. Now, the f here always refers to the name of the function, but it stands for the rule. The very, very specific rule here. Now, for example, in this case right now, the rule is that I'm going to multiply the independent variable by 2. That's what f stands for. F, in this case, literally means multiply the independent variable, hopefully you can see that, yeah, by 2. That's what the f in this function notation means, very specifically, okay? Now, what's inside the parentheses here, this is the independent variable. So f means multiply the independent variable by 2. Whatever's inside here is the independent variable, so that's x. So the result is multiply x by 2. That's the result. So this is what the function does here, okay? So you need these two pieces together to create the dependent variable. The f represents the rule as to how the dependent variable depends on the independent variable. And then whatever's inside here identifies very specifically what that independent variable is. Now it can be, if you use x, then we're talking about the relationship in general, but you can plug specific numbers in there to get specific points as a result. And then what happens here, if you plug a specific number in here, then the result is going to also be a specific number, and it's going to be the y coordinate given that x coordinate. Okay? So let's just kind of read through what's being said here. So remember that y is equal to f of x. That's because f of x altogether is the dependent variable. So f of x is y here. And it's like a machine. It really is. This is a great way to describe it. It's like a machine. You have an input value, okay? That is your independent variable here. And the function changes it and spits out an output value. That's the y value. And remember that whole thing there, that whole thing is the dependent variable. That is equal to the value of the dependent variable. So little note here, it's an important one. I've watched students who are unclear about function notation make this mistake a lot here. The brackets in f of x are not multiplication. They are not multiplication. This is all one symbol, and it takes some getting used to. Okay, this is not f multiplied by x. Please don't think of it like that. That's not at all what that means. Okay, I know it looks like that. Okay, but it's context specific. This is like sometimes words that we use that sound the same, homonyms, okay, that sound the same but they have different meanings. Like our words, for example, two. They all sound the same, but they're three different words here, okay? That's kind of what's going on here. I know what I mean in context, okay? So it's the same sort of thing here. So this means that the function y is of a value or at a specific value of x. Now, usually when it comes to functions, we're going to use letters that are like F, G, and H, usually from around that part of the alphabet. That's usually where we grab those letters from. They can be any letter in the alphabet, really. But usually we use the letters F, G, and H for functions. Okay? And so just another example here. So f of x equals 3x minus 9. Remember that what this means here, what the f is, f stands for, okay, multiplies the input by 9 and subtracts 9. That's what the f means. And then what's inside the parentheses? This is my input. So multiplies the input by 3 and subtracts 9. Well, if the input is x, multiply the input by 3x, and minus 9. As soon as you start to use different letters, that typically implies that we're dealing with a different type of relationship here. So this also serves another purpose here. If I've got multiple graphs on a grid, I can now tell the difference between them. It's not always y equals y equals y equals. Well, now I've got an f, I've got a g, I've got an h. So this serves multiple purposes. It's an extremely powerful bit of notation. Okay, so let's take a look at a handful of examples related to this function right here. Let's zoom in a little bit. So f of x is equal to 4x minus 2. So let's identify what f stands for here. F means multiply the independent variable by 4 and subtract 2. Okay, that is exactly what this is telling me about the relationship between x and y. Okay, f of x, the dependent variable, is going to be multiply the independent variable x there by 4 minus 2. And I know x is the independent variable because it shows up in here. So now we do this here. So the question is, what is y when x is the given value? So f of 3, what is f of 3? Remember, f stands for multiply the independent variable by 4 and subtract 2. Now the independent variable is 3. So multiply 3 by 4 and subtract 2, and the answer is 10. And so this gives us a relationship here between x and y. So I know that the point 3, 10, okay, is on the graph. The value of the independent variable, that's x, and the overall value is the dependent variable, y. Here, this is saying f, remember, f stands for multiply the independent variable by 4 and subtract 2. In this case, the independent variable is negative 1. So multiply negative 1 by 4 and then subtract 2. Well, 4 times -1 is -4, minus 2 is -6. And again, what this is saying here is that the point -1, -6 is on the graph of the function. Now finally down here, again, f stands for multiply the independent variable by 4 and subtract 2. The independent variable now here is 10. So 4 times 10 and then subtract 2, and that's going to get me 38. Okay, and again, that means that the point 10, 38 is on the graph of that particular function. Now we can look at the same relationship in a slightly different way, and I hope you see the difference here. In these questions coming down here, I am asking what is the value of the independent variable when I know the dependent variable is -14. So remember that f of x, f means multiply the independent variable by 4 and subtract 2. It's just that in this case here, the independent variable is x. So this means 4 times x minus 2 is equal to -14. Well, I can bring the 2 over and make that 4 times x is equal to -12. And then when I divide, I'm going to get that x is equal to -3. Okay. Same thing here. F of x is equal to 2. Well, I don't know what that value is that's producing the 2, but I know how to interpret this. F means multiply the independent variable by 4 and subtract 2. In this case, the independent variable is x. So multiply x by 4 and subtract 2, and that's going to get me 2. Now, I know that I keep saying this over and over again. I'm just trying to, again, re-emphasize the pattern here so that you don't forget it. So here, 4x minus 2 is equal to 2. Bring the 2 over. So 4x is going to equal 4. Divide both sides by 4, and I get 1. Here, f of x is equal to 0. Notice that I'm not making, the 0 isn't inside here. There's an x inside here. F means multiply the independent variable by 4 and subtract 2. The independent variable is x. So 4 times x minus 2 is equal to 0. Add the 2 to both sides, and then divide by 4. And when I divide by 4, I'm going to get that x is equal to 1/2. So notice the difference between these sets of questions. Here, I've replaced the x with a number. In fact, I don't even see the x show up at all here. Okay, I'm plugging in values here. Here, the x does show up because that's the thing that I'm looking for. Okay, so you really want to kind of clue into the difference between these two sets of problems here. Okay, so now in this little section here, we're going to take a look at the graphs of linear and quadratic functions, and we're going to throw a few more in here just as something to compare to here. So we've already seen in the previous example that when you've got a quadratic function, a linear function, that they're going to have different shapes when you graph them. And so now what we want to do here is we want to go through and have a quick look at that, look at what the different functions do, kind of get a sense of the kind of graph that we can associate with each one of these equations here. Now I've already hinted at what happens when you've got a square on there and when you don't, and the fact that it's the degree of the function that affects the graph here. But anyway, I'm going to use this opportunity we're going to go through these graphs here, but I'm going to show you something on your calculator as well that you may not be aware of. So I'm going to go through and graph each one of these things. So I've already got most of the graphs here programmed into my computer, and I'll show you how that's from my calculator. I'll show you how that works. So when I press y equals, I've already got most of these equations plugged in there. So I'm going to zoom in here. Now, right now, if I was to press graph, I don't see anything. So I'm going to go back to y equals here. What you got to do is you're going to move the little cursor over to the equal sign. I'm going to press enter. And what that's going to do is it's going to darken that one in. And now that is the active equation. Most of the time, by default, these are all turned on. And so whatever you enter in here gets graphed automatically. But I've turned most of these off so we can just see them one at a time. So now when I press graph 3x plus 1, okay, I get a graph that looks like that. And if you think back to a previous course here, you probably recognize that as having a slope of 1 and a y-intercept of, a slope of 3 and a y-intercept of 1. And so that graph looks something like this. Okay. And now I can very quickly move to the second one. I'll go y equals. I'll come over here, turn this one off, come down, turn this one on. So negative 2x squared plus 5x plus 3. What does that look like? Okay, so it's a parabola. Okay, it's this parabola that comes up and then goes back down like that. Something like that. At least you get the idea. Okay, this what we call this parabolic shape here. Next one, go back to y equals, come down here, let's turn this one off, turn this one on. Now this is negative x cubed plus 1. Now we haven't talked about what happens if you've got a cube up there, but let's take a look. Okay, so that does something a little weird. It comes down like this, kind of levels out and then drops back down again. Okay, well that's not like the line or the parabola. That's something a little bit different there. Well, that's interesting. Let's take a look at the next one. Oops. Go up here, turn this one off. Let's turn the next one on. So this looks like another quadratic here. Whoops, not coming through clear. Press graph. Oh, okay. So now this is a parabola that comes down. And just even by a quick glance at this, notice that it goes through has a y-intercept of negative 3. It comes down and the minimum value is negative 3. Well, when I look at the equation, there's my negative 3 right there. I suspect there must be a connection between that number and the fact that the lowest number that this gets to is negative 3, or the fact that its y-intercept is negative 3. Interesting. We'll talk about that in a little bit here. 1 over x squared. Let's take a quick look. Whoops. Sorry, go back to that. Okay, turn that off. 1 over x squared. Well, this is going to be interesting. Oh, look at that. Now that is a unique looking graph. So the graph appears to kind of ride along the x-axis here like this, and then it shoots up, and then it comes back down, and then seems to go along the x-axis again. Now it's easier for me to see this. You're probably not seeing it as clearly here. There's a bit of a green line that runs along the x-axis. For some of the older calculators that aren't color, you probably don't even see this part here because it gets so close to the x-axis that the calculator can't differentiate them. But it is there, and it's just a little bit above, and then the closer I get to the y-axis, the larger that difference gets until, boom, it shoots way, way up there. We'll talk about what's going on there a little bit later. The next one, x squared plus x plus 1. Okay, so we come down, oops, turn that one off, turn this one on. What does that look like? Okay. Oh, that's interesting. And notice that this parabola here, this shape, doesn't even touch the x-axis. Okay, that's significant. Okay, that means something special about this particular graph. But right now, we're really more interested in just the fact that it's creating this parabolic shape. Okay, 4x, y equals 4x. Let's go down, turn that off, go down to the next one, turn that on. 4x. Now that looks vaguely familiar. I've seen that in a previous course, and yeah, that's just a straight line with a slope of 4, and it goes right through the origin. Next, 2 to the x. Well, now that's different. That's different. Notice that now the x isn't in the base of this power. In most of the quadratics, even if I go just above it here, x is in the base to the power of 2. This is now 2 to the power of x. Okay, we would probably call that exponential. We label these functions based on where the x is. And so in this case, exponential seems like a good name for that. What happens when I graph that? That's probably a little bit clearer depending on your screen here, but again I can see this blue line that rides along the x-axis, and then it swerves away really, really quite quickly once it crosses the y-axis. So it rides along pretty closely here, and then it shoots up like that. Okay, something to take note of. Negative 2/3 x minus 2, y equals, so I'm going to come down, turn that one on, negative 2/3 x plus 2. Now, based on what you've seen in previous courses here, you might suspect that this is going to have a slope of slope of negative 2/3 and a y-intercept of negative 2. Oops. Oh, what did I get wrong here? Oh, sorry. Actually, this is a good opportunity. So I made a blunder here when I entered that in. This is a good opportunity to talk about it. I used this button here without thinking when I should have used the negative sign there. So I'm going to do that right now. And now press graph. Now, did you notice that when it said error, I had the opportunity of having the calculator take me to where that error was. That's a great little feature of the calculator here. Press graph. And there we go. Slope of negative 2/3, y-intercept of negative 2. So that's going to look, whoops, put that off the graph there. It's going to look something like that. Okay, now the last one that I've got programmed in here, because I only have room for 10, is y equals x. And that right there is just a basic linear function, slope of 1, y-intercept of 0. So it goes straight through like that. Now let's take a quick look at this guy right here. So now I'm going to come down here. I'm going to turn them all off. And actually what I'm going to do now is just clear them all out. Oops. I got two more to enter in here. X squared. So x squared, press graph. And there's just your basic parabola. And then finally, and I'll just change this, I'll make this x cubed minus x squared. Okay, let's see what that looks like. Now this one had a square in it. Okay, but look what it did here. But the shape that I got here was not a parabola. Kind of bent down and then went back up again. Looked more like that. Okay? So that's not a straight line, but it's also not a parabola here. Okay, now I'm going to zoom out here. Let's have a look at what these graphs all look like. Okay, so you can see them all here. Now in the next little section here, I want to identify the graphs here that are linear and the ones that are quadratic. Okay, so it might be, well, okay, actually, I tell you what. I'm just going to write out the equations. I'm going to kind of zoom in on this a little bit because I was going to do this a slightly different way here, but it might make more sense to do it like this. So from our graph here, the ones that were linear were the y equals 3x plus 1. Okay, that was linear. The y equals 4x. That was linear. Y equals negative 2/3 x minus 2. And y is equal to x. Okay. So all of those were linear, and we're going to take a look at what makes those unique compared to the other graphs here. My quadratics were y equals negative 2x squared plus 5x plus 3, y equals x squared minus 3, where am I at here? Y equals x squared plus x plus 1. And the last one was y is equal to just that basic x squared. And then the graphs that were neither linear nor quadratic, negative x cubed plus 1, and you can even hear it when I describe that's different. The other one was y equals 1 over x squared. Okay, we'll talk about that in just a second here. Y equals 2 to the x. And even when we got to this one right here, that one looks substantially different, and we even talked about that. That's what we call exponential. And then this other one here, y equals x cubed minus x squared. Okay, so we can tell from the equation whether the function is quadratic or not by looking at the degree. Okay, so a function will always be, quadratic function will always have a degree of, and here's the big thing, 2. A linear will always have a degree of 1. Okay, so the largest exponent on a variable, whether it's the independent variable or the dependent variable, the largest exponent is going to be 2 if it's quadratic and 1 if it's linear. Now, if the 2 happens to be on the y, then it's a little bit different, okay? In fact, that changes things substantially. So for right now, for us, we're really thinking about the degree on the x, on the independent variable. Now, just for funsies, so let's take a quick look through here. This one was what we called cubic. Okay, and that one looked like this little kind of twist to it. This one here, 1 over x squared, you might look at that and think, well, wait a minute, that's got an x squared in it. Shouldn't that be quadratic? But because it's in the denominator, we actually call this one a rational. And it turns out the fact that the x is in the denominator makes, well, I should say it like this, that is more of the dominant feature of this particular function right here. And when we took a look at it, this is what we got here, this kind of a strange sort of graph that rides along the x-axis and then shot up right at the y-axis there. Then we had the exponential one. We talked about that one, and we call it exponential because that's where the x is in this particular function. And we saw what that did. It rode along the x-axis, and then once it crossed the y-axis, it went up. And then this last one here, just like our first one here, even when I describe what we're writing in here, I use its name. It's x cubed minus x squared. That's the largest exponent is a 3 on the independent variable, so it's going to be cubic. This is the term that dominates how this particular function behaves. Just like here, this is the term that dominates how this function will behave. So, without graphing, let's take a look at these guys down here. So, are these going to be quadratic or not? And this one right here, because the largest degree is 2 on the x here, this is definitely quadratic. Whereas over here, I do have a quadratic term, but I've got this x to the 5th here. This actually makes this one what we call quintic. So this is not quadratic. The dominant term here is the x to the 5th, not the x squared. Over here, 3 minus 2x minus 1/2 x squared. Sorry, 1/2, 1/5. Okay, I can see what that is. It's 1/5. The x squared here, this is the largest degree term, so this is going to be the dominant term. Okay, that's not in the denominator. Okay, this term right here could have been written as minus x squared over 5. So the x squared is in the numerator here, and this is definitely, as a result, quadratic. Okay, so I hope after this you get a sense of what a quadratic function is and what they look like. Okay, we keep throwing around that word parabola. We're going to have a quick look at some the features of the graph here in just a little bit.